in this particular case, right, we would then check this and we would do the thing, you know, is it 2 or bigger? Right? Remember how we were talking about is it 2 or bigger? If so, we were going to increment. The way you could do that is when this comes out, you'll end up in our case with, you know, you get an x point, x, right? You get these, I can take the most significant bit and I can run it into here to determine should I increment or not. Right? And that will go into my exponent. In our case, it's 0, 1 point, right? So it's a 0, so I don't increment. So the number I calculated goes straight through. So 129 minus 127 gives me 2, plus 128 means I store 130. 128, no 64s, no 32s, no 16s, no 8s, no 4s, 2. So I get 130, which is 129 minus 127 plus 128, which is that sequence here. And then it didn't end up being the increment because the digit here was a 0. This digit is a 1, it's the hidden bit, we chuck it out. All the other digits come down. So in our case, that's the hidden bit. Those are the digits I store. So that's 1, 1, 0, 1, 1, 1, and the rest all zeros. Make sense?
Yeah.
So, and then you could go back and check to see is this one correct. So this number we know is 1.11, 0.111 times 2 to the, this is 130 minus 127, so a third. Right? So that means this number, shift the radius 0.3, 1, 1, 1, 0, 0.111. Right? So that's 14 point, or we could say 7/8. That's 7 in the 8th place. So that's 14 and 7/8. Now we could just check that. 3.5 times 4 1/4. That goes on. All right, so I can go 4 times 3 gives me 12. 4 times 1/2 gives me another 2, so that's 14. And then I get 3/4 plus an 8. Right? 3/4 is the same as 6/8. 6/8 plus 1/8, 7/8. It's the same.
Cool. Yeah.
Good?
Thank you.
Okay. So, for forwarding, I'm not going to build the whole circuit right now because you don't need to know that because you have to have the rest of the pipeline. And so, to do the whole forwarding thing, you need to have what we're going to do in chapter 4.
Okay.
Okay? But I can give you what the basic idea, because we have hit this much of it that's going on. We've noticed the need for forwarding and the idea of forwarding. We just haven't figured out how to build the circuit yet because we don't have everything else that goes into it. So when you're looking on these, let's say for instance I had just a very simple sequence of commands. So I'll just do a sequence of something, I don't really care what it is. Add. So let's just say I have these three commands. I'm going to call this command A, B, and C, so I don't have to keep writing them out again. For every command, I have to fetch, then decode, then execute, then memory, then write back. Now, at time 0, I'm going to load or fetch my very first instruction. So I fetch A. That's going on. I don't care what else is in there, we'll assume it's no ops. That's going on. At time 1, A goes to be decoded. At decode, it figures out it's an add, and it also gets the value of the S zeros. Okay? Now, those are whatever they are, right? So I might have a table over here just to hold my memory, S0. Let's say we're going to use T0, we use T1, we use S3. So let's say this was 4, and who cares, this is -3, and this is 29, and S3 is, here's 14. Fine, just pick some numbers. Okay, so when it goes and does this, it finds out my two numbers are both 4. So it knows at this point that this is going to be 4 plus 4. It hasn't done it, but it knows that's what that command is. It's got the data for the 4s, and it knows it's an add. Now, at the same time it was doing this, it was fetching B. Simultaneous. That's the idea of a pipeline. It's going to do it concurrently. When it goes to the next cycle, A goes into execute, and it's going to do 4 plus 4 and figure out 8. B is going to go to decode. It's going to figure out it's an add, and it's going to say, oh, I need T0 and S3. T0 is -3, and S3 is 14. Do you see a problem? What did you mean when this was going on? You meant that whatever it calculated here is going to go add. Right? But that calculation is here in the execute unit. It hasn't made it back to the registers yet. Right? So it hasn't made it home. Since it hasn't made it to its home yet, you can't find it. So on a regular system that goes on, you'd run into a problem. So this is what we call a data hazard. This particular one is, I'm doing a read after a write. So we call it a raw, R-A-W, read after write. That's going on. And the problem is that it got this old value of -3 instead of the new value, which should be 8. So the question is, could I get the correct value there? Well, what forwarding does is forwarding says, hey, look, I know where this 8 is here. So at the next stage, when B is going to go to the execute unit, I can take A's value of 8, and I can just pass it right in to replace it. So that I end up getting 8 plus 14. So they sometimes draw it this way, they might draw it this way. That way it matters.
So does that happen instead of, like,
So
what would
the way that we do it is, if you kind of picture the unit, we built the fetch unit. We just kind of draw that as a circle, and then we have the buffers. And then we have the decode unit, and we have their buffers.
Yeah.
And we have the execute unit that's going on. And the execute unit's going to have 2 values that are coming in. That's these 2 that's going on. And then I've got the next one on here that's got the result, right? So this has to go into a little adder or an ALU. It's going to give me my result.
Yeah.
I can take this result, I can run it backwards, and I can stick some muxes here. And I can say, which one do you want to go into? And in this case, I want to replace the first one. So I have a control unit that goes, oh, the actual answer is right here, and this is where the 8 is. So I just run it back, I now have it right here on this mux. I just set this mux and say, oh, grab the other one, and the 8 comes in instead of the 3. So I just swap them right at the gate. So I have to put some muxes in, I have to do some control circuitry to figure out where that is. But that's what we do with forwarding, is we just take it and we just run the value backwards 1 step, or 2, depends how far it is, as it's going on. And then, of course, C was coming in, and C is gonna have to be decoded, and it would need that same pathway that's going in. But basically, we just use a series of muxes just before the execute, and we swap the correct value in just in time, because it's already there.
So if that's a data hazard, what's a control hazard?
The control hazard is when you deal with a branch.
Okay.
So like if you had a statement that was like if, right? If I say, if X is greater than 7, it's a control thing because it could go one of two different directions. It's a hazard because you don't know whether that's right or not. What if you pick the wrong way? Right? So control hazards always have to do with branching in some sense.
So is there going to be a control hazard on any time you like branch?
Anytime you're branching like that, and if, it's the same thing happens inside a for loop, right? Or X equals 0, X less than 10, right? X plus plus. There's a check. Anytime you see that check that's going in, it's a control hazard. Because as long as X is less than 10, you should stay in there, which means you're going to jump back up to the top of the loop and keep repeating. But if X is 10 or bigger, then you won't. So which way do you go? Well, until you've done the check, you don't know. But the check takes time, and that causes other things to be delayed. It'll be much faster to take a guess, but your guess could be wrong. Right? But it's faster to be wrong and fix it than it is to be right, but really slow. And we're just concerned about speed. So that's what we call control hazards. So whenever you see branch commands, just the second you see a branch command, you should think control hazard. Right, so if you see BR and then anything that follows it, right? That BR means branch. Right? What comes after here tells you whatever it is, right? Branch equal. Branch equals 0, right? It's, I mean, any of those, this is just telling you what the condition is that's going on. But this told you that it was a branch. If it's a branch, it's a control hazard. Because you have to figure out what's that. And based on it, you either branch or you don't branch. Does that make sense?
Yes.
Does forwarding make a little more sense now?
Yeah.
Right. I think the easiest way to remember forwarding is just think of it like the associate with call forwarding, right? You're forwarding the data you want to get to where you are right now. So we're literally forwarding the answer to where you are now, allowing it to kind of track your command through the execution pipeline. And we have to give circuitry that allows it to track it, and how do we know it's your phone, and make sure we connect the call up right, and all the rest of that. But that's all control stuff, right? Which we will get to, after spring break.
Can you go through the steps of conditional sum?
Sure. I did one earlier, so there'll be another one at the beginning of the tape if you look at it, but I'm happy to go through and do more. And there should be another one that's also online as a video. Inside, if you look in the My Media section, which is where this is going to appear a little bit later. How about you guys give me numbers? The one they did earlier was 3 and 5. So I'd rather not do 3 and 5 because you could always go back and look at that one.
7 and -8.
7 and -8. Okay? So when I'm doing 7 and -8 that's going on, do you want me to do this as 7 minus 8?
Yeah.
Okay, so I'm going to do subtraction. So when I'm doing subtraction, we do subtraction by flip the bits and add 1. Right? So 7, we know is, now 8 is that, and then I'm going to flip the bits, and that's my number. and I need to add 1, which I can do by setting the carry into 1. Fair? Okay. So when we're doing conditional sum on here, for each one of these digits, we're going to treat them as completely separate. So I can do them in whatever order I want. I'm going to generate a series of these kind of like little parentheses with commas, because this is how I'm going to store the intermediate results. All except for the very first one. I'll explain in 1 sec here. So what do I mean by in here? This is going to be the numbers above them added go right here. So this is the sum. And I'm going to assume there was no carry. And it's going to be the sum, and I'm going to assume there was a carry. So I'm going to do this calculation both ways, with and without the carry being set. Those are the only 2 options. So I have now exhaustively done every possibility. All right, so that's the whole trick to this, is I just exhaustively do all the possibilities. I don't need all the possibilities here because I know the carry bit in advance. Since I know it, I might as well take advantage of it while I do the extra work. And then I will know what all the possibilities are, and I'm just going to group them together. Fair? Okay. So I'm going to work on these, but I'm going to, just to prove that I don't need them in any particular order, I'm going to literally sum them in weird orders. Right? So I'm going to do this one first, because I just feel like it. Right? 1 and 1 gives me 2. That's the sum plus nothing. The sum plus 1 would have been 2 plus 1 would give me 3. I feel like doing this one. So 1 and 1 gives me 2 again, and if I'd add 1 it would be 3. I'm going to do that one now.
Did you mean to write 3 in?
Oh, I did need to write 3 there. Thank you. All right, 0 and 0 gives me 0. If I had added 1, it would have been 1. 1 plus 1 plus 1 gives me 3. So I know that one exactly. Now, this is the carry bit to the next stage, right? Because it always comes up, you add the numbers, you get the sum and carry. Right?
Yeah.
So this is the carry bit. That's what I should have picked here. And that means it was plus 1, not plus 0, so it's this one. So these 2 numbers, if I look at it, this is what if the carry had been 1, what if the carry had been 0? Well, I know what the carry is now. So I can just put into a selector, and these 2 bits come out. That's the sum bit, it doesn't change. So I'm going to group them together. Make sense?
Yeah.
So the 1 comes down, and then this was a 1, so it selects this, so I get 1, 1. Now, I'm going to do this thing right here. I'm going to just rewrite as a single box going in. Is that fair? So I take these 2 things down, and I take both of these, and I run into the box just like I did here, and out comes my 2 digits. I do the exact same thing. The 0 carries through, the 1 selects that, which gives me 0, 1.
But how does it, I'm not going to do this wrong, how does it know which one to pick on that?
I'm going to do both.
Okay.
Fine. I've only done the first one. So I also have to take these 2 and both of these, and I run into, again, an identical system. And the 1 comes through, and this one selects that, which gives me 0, 1. And you'll notice that's 3 and that's 2, so they're always off by 1. This is always bigger by 1. So I just do both. And this is just so that I don't have to redraw that whole circuit multiple times. And that just gives you an idea. I just take it and stamp it, which makes it nice and easy. Now notice, this is the carry bit. Those are the 2 sum bits. Now I know the carry bit. Now this had been, what if it had been 0? This had been, what if it had been 1? That's the actual carry bit. Wow, it's the same stupid box, just slightly different number of wires in it. So I really could just duplicate the box again. The 2 bits come down. This 1 selects that.
So it just speeds up the whole process because it's less number of cycles.
Because it's less steps that goes on. Now, if you think about it, here's my answer, and I got all 1s, that's the carry out. So I did 7 minus 8, which should have given me -1. What I got was 1, 1, 1, 1, which is -1. Now, here's the fun part. To do a full adder, which I needed here, and I need for that step, and that step, takes 2 gates deep. So this cost me 2 gates to calculate this level. A mux takes 2 gates, and that's all I've got here. So I've got 2, 4, 6. Cost me 6 gates.
And what would it cost a bunch to do it in sequence?
If I had done it sequentially, it'd be 2 at each step carried on. So it would have been 8. So at 4 bits, the conditional sum cost me 6. And your standard ripple carry would cost me 8. Pretty close. If you go to 8 bits, this would happen in parallel right next to it. And I just have one more mux level to combine them in. So it would cost me 1 more mux. This, you'd have to ripple through another whole 1, so twice as much.
Yep.
If you go to 16 bits, I'd have 2 of these in parallel with 1 more mux. It'd cost me 10 gates. This one would take twice as long, so it'd go to 32.
Yeah.
All right. So to get up to a standard one that goes in, this is doubled again at 64, this is only at 12. So you can start seeing as the number of bits increases, it gets tremendously different in its cost, which is why conditional sum is so neat. I mean, we're doing it for small cases because we're humans. I don't need to spend all the painful time doing those. Once I realize, oh, every new level I can take twice as much before, and I just have to select between 2 things, and it's a mux. Pick between 2 things.
Would you ask, should we know the clock cycle and ripple
Nah, you
cycle?
can figure it out. I do this because you could compare them as go, and I want you to have a feeling for what's going on. All right? But you notice, like, if I was just dealing with 4 bits, there's not a lot of advantage. Right? So if I was just dealing with something really tiny, I might do a ripple carry. Because who cares? It's just not going to take that long. But notice pretty rapidly, you know, once you're 8 bits or more, it's, you know, not even in the ballpark. So.
Yeah. So, I know it's not all about the test question, but a test question on this would maybe be like, you know.
If I was doing something like this, I could for instance give you some numbers and ask you to add them.
Using.
Show me how you would do it adding conditional sum, which I think is one of the sample ones that I did.
Yeah.
And you'll see when I do it, rather than writing all these things out, all I usually do is just take those 2 together. Those 2 together, generate these. Those 2 together, generate these. I usually just do it as kind of like a, just replace this by, right? Combine those 2 to generate that. Right, because you don't have to draw the circuit every time to figure out what it does. But eventually you want to be able to draw the circuit. other questions? We good?
So like on the first homework, we had like a bunch of problems with like all the CPI equations and stuff.
Yep, I could ask you performance.
Okay.
Because technically speaking, once we get down to gates, right? A gate takes a certain period of time. That's kind of a standard delay. And then it looks at your logic family. So for instance, I can look at a logic family and say, oh, my gate cost me, 100 picoseconds. Right? And I could say, oh, I'm adding 16-bit numbers, I'm going to do it by a conditional sum, right? So if I was doing it on conditional sum, that would be 1,000 picoseconds, which is a nanosecond. So I could say, oh, for 16 bits, if I was doing a conditional sum, I would have 1 nanosecond. If I was doing it by a ripple carry, I'd have 32 times that. So therefore I'd have 3.2 nanoseconds. So that's 16 if I was doing it ripple carry style. That's now a time delay that goes in. So I can take a look at a penalty. How much longer would it take in it? I can look at my clock cycle time, I can figure out how many clock cycles that is. So if I had a 1 gigahertz clock, for instance, right? 1 gigahertz clock is 1 nanosecond. That's 1 clock cycle, and that is 3.2 clock cycles. So I could say, okay, that would mean in here, addition would take 1 cycle. This one, it would take 3.2 cycles. I could say what would be the performance difference if addition was 30% of my commands. Does that make sense? Okay. Right. I just take what was my timing, given that I gave a gate size to it, 100 picoseconds each. I could figure out what they are, knowing that's a 1 gigahertz clock. Gives me 1 nanosecond per clock cycle. So that's 1 clock cycle, that's 3.2. I can just say, hey, what's the performance? Assume everything else is fine, they're all 1. What's going to be my performance situation? What's going on? Well, I know most of my commands are going to be speed 1, so I can do them for conditional sum first. So I can say the rest of the commands are 1. Addition is a 1 for me. I was able to fit in 1 clock cycle. I know these are, like I said, 30%. That means this is 70%. For ripple carry, that would be 3.2 cycles. And everything else we're leaving at 1. Just for comparison, I could say, what would the average CPI for this system versus that system be? Well, let's average CPI is just the cycles for this type of instruction times how frequent, plus this one times how frequent. So I would have for the conditional sum, I'd have 0.3 times 1 plus 0.7 times 1. So I get 1. For this one, I'd have 0.3 times 3.2 plus 0.7 times 1. And I've got what? 0.96 plus 0.7. That gives me 1.67. Doing that arithmetic, at 1.67. So I could see the CPI, if I was doing conditional sum, is a 1. If I'm doing a ripple carry, it's a 1.67. That's tying right back to those performance errors. Now I got CPI. Right, so I could say using those percentages, assuming I was doing 1,000 instructions, right, on my 1 gigahertz clock, how long would it take? The time is equal to the instruction count times the CPI divided by your clock frequency. Know all those numbers now. For conditional sum, we said it was 1,000 instructions, CPI was 1, and the frequency is 1 gigahertz. Let's carry on. All right? So, 1 over a gigahertz is a nanosecond. So I've got 1,000 nanoseconds, which is 1 microsecond. They'd say, oh, for 1,000 instructions on that machine, it'd take me about a microsecond to calculate it. What if I was on that machine? All right, so ripple carry, same exact calculation. Well, the time on that machine would have to be still 1,000 instructions. Now it's 1.67 that's going on. And again, we're going to be dividing by gigahertz, which is the same as multiplying by a nanosecond. Save ourselves the time. So I've now got 1670 nanoseconds, which is 1.67 microseconds. If I could look at those in between these two, this one takes 67% longer. Right? So I can look and I can think directly from how did you do that on one portion of the system, and by making some assumptions about the rest, I can tell you what the overall system performance is going to be and what it runs like. So then you can make, at this point, you can now make a judgment call. Is it worth taking out your ripple carry adder and putting in a conditional sum? So we're 67%. Depends how much cost put in, right? I mean, but as long as it's cheap, it's probably worth it. So that kind of walks you through where does this kind of low-level stuff we're dealing with deal with the early portions. The early portions give you the structure to be able to analyze that and say, how does that little bit fit into the bigger scope? How do I know, do I want to do this or not? Does that make sense? Have any more questions? Awesome. Well, good luck all. I'll see you all tomorrow.
Thank you.